I want to welcome everybody back to our podcast series we call Lime Time in Texas. And today I'm going to answer a question about what is a lime series test. There's a few things that we know about lime. So lime, when you add lime to a clay soil, there's two or three things can happen. So typically, as soon as you add lime to a clay soil, it starts to dry that clay soil out. Once you get that pH above 7, it starts rapidly drying that soil. Once you get the pH up to about 10, we start to what we call it modifying the soil, where you start to see a breakdown in the plasticity index of the soil. We start to see a textural change where you have the process of flocculation and agglomeration in that soil, really seeing that breakdown in those big clay particles, the clods of clay, to seeing that textural change and a volumetric change also. When we get up above a 10.5 all the way to 12.4, that's the zone we call this kind of the stabilization zone. So when we design a lime stabilized subgrade, we are trying to put enough lime into that subgrade so that we get the pH up to 12.4. And what we know throughout history is, and what the data will show, is that once you get it to 12.4, it'll never go back down below 10.5. So let's talk a little bit about, kind of how we get to that point. First of all, I'm going to go back to our definition of stabilization and what our goal is here. So what we're trying to do when we stabilize a clay soil, not just modify it, we're actually trying to stabilize it where it's a long-term, it's a permanently alter that clay soil to where you get permanent strength over time. And there's a certain amount of lime that we can put in there that we know that we're going to maintain that pH up above 10.5, and that permanent strength gain will continue to go up over time. There's a chart that we've shown several times in several of these podcasts, and I always go back to this one, talking about the solubility of silica and alumina. If you look at this chart here, what it shows you is that at a pH of about 7, which is where most things happen in nature, which is a neutral pH, alumina and silica are not very, very soluble. Once you increase that pH up to, and you see right about 10, you start seeing that the solubility of the alumina and silica starts to go way up. Now keep in mind that all clay is made of alumina and silica. So our goal really is to solubilize that alumina and silica. And if you look at the chemical equation here, it's going to show that what our goal is to try to take calcium, or calcium hydroxide, add it to that silica and that alumina, and form pozzolanic cements, which we refer to as CSH, or calcium silicate hydrate, and CaH, calcium aluminate hydrate. So that's our end goal, is to get to that point. Well, a lime series, and this goes by different names. It's really the way that you determine the demand for the lime in that clay soil. If we look at TxDOT's test procedure of 121E Part 3, this is also known as the Eades-Grim test or Eades-Grim pH test. Some people just call it a pH series, but all it does is determine the lime demand. If you're using this test procedure, you start off actually using Tex 128E, which is the method you use to prepare the sample. It's pretty simple. You basically take 30 grams of the soil that's passing in number 4 sieve. You mix it with about 150 milliliters of water that's got to be deionized or distilled water, and you stir it about every 15 minutes for up to an hour, for 1 hour, and then you run what we call just a pH test on it in different increments. So here's kind of what that looks like. If you see here, we're going all from 1% up to 10% lime concentration in those different solutions there, with the 30 grams of soil in there. And again, you just stir them up, and then we measure the pH after that 1 hour of processing that. If you look at what the pH series does, is you'll quickly see the pH goes from a 7 value, or roughly 7, jumps up real quickly when you add lime, because keep in mind, lime has a pH of right at 12.4. So our goal here is to get that lime, the pH up to 12.4, knowing that it will maintain that. That means that it's got enough lime in it to maintain that over the life of that subgrade. So you can see here, and it's a very, very sensitive test. It doesn't take a lot of lime to get that pH to start jumping up. In this example here, though, according to the test procedure, once you get to 12.4 pH and it starts to repeat, and you always have a little bit of test error there within about a hundredth or so there, but you can see there, once we got to 6%, it was only going up to 100 at a time. So in this particular case, we would determine that this soil needs 6% lime in it to have enough lime supply in there that it's always going to form that pozzolanic cement, and that reaction will go from now on, that it's just a continuous reaction, that there'll always be enough lime in that there. So here's what we want this to look like. At the end of this, we're taking something that's a native clay soil that, again, I always use the meatball analogy here, but it kind of looks like meatballs there. So that's really millions and millions of particles of clay soil that are clods there. Once you treat it with the lime, and this is what it looks like in the lab, it's going to look like a sandy soil or a very granular soil. So it becomes what we call very friable. It's very workable. That's one of the goals that we have. But what you don't really realize here is that lime on the right-hand side, when you see the lime-treated clay, that is actually a pozzolanic cement. Now, it doesn't look like it at this point, but once it's compacted in the ground and over time it's going to continue to gain strength, eventually that's going to look like a lean concrete in that soil. So, and that, again, is one of our overall goals, is to give it long-term permanent strength. This is what it looks like in the field. Again, taking these clay soils here that are highly expansive, that are very difficult to work with, that cause all kinds of problems, that shrink and swell and crack, make it into something that looks like the picture on the right, where it looks like a very granular soil. And very simply, that's what our goal is. So the design procedure is called a lime series. It's very simple to run. It takes about 3 days to run that sample. You actually start with about a 50-pound sample that you bring to the lab and break it down into 30-gram subsamples to run the test. But there's not a lot else to it. I will say that when you're building a project on a very big project, you will probably want to run more than one lime series. Let's say if you're going 20 miles down the roadway and the soil changes from, it can go from being a really fat clay to more of a lean clay, or even get into some sandy soils or things like that. You want to identify what you have and take soils that are representative of that whole project. So it's very seldom that on a very large project that you're going to have just one lime series. You may have to run them over time and over a different distance to make sure that you account for that. So there may be one part of the project that needs 4% lime or 6% lime, and the other part may need 8% lime. I was doing a seminar in Austin District about last month, and they have areas that are west of the interstate that need 4% lime. East of the interstate, it goes up to about 8% lime. So you can't just assume that all clay soils are the same. So that's really the point of running these tests, is to define what that lime demand is. Thank you for watching this episode of our podcast. If you want to learn more about the use of lime, reach out to us on our website at limetexas.org. You can also email me at dalerand@limetexas.org. And please follow us on LinkedIn and subscribe to our YouTube channel. Thank you for watching.